Okay, so now we're going to be talking about crossed fields and the discovery of the electron. So when we were talking about electric land and magnetic land, you noticed that there's an electric field, there's a magnetic field, there's also Fe, and there's also Fb. And you're like, oh, well, I wonder what's the commonality between them. Well, they both act on charged particles. And if they both act on charged particles, then that means that they can also sort of, kind of, interact with each other. If only through that connection with the particles. So what happens is, so when E and B, basically, when the electric field and the magnetic field can both act on charged particles, when E is perpendicular to B, that is not a B, when E is perpendicular to B, we can call that a crossed field. So, imagine you are a really, really old guy named JJ Thomson, and you're kind of bitter and tired with your mediocre life, and you want to do something really cool, so you design what is later to be known as the Cathode Ray Experiment, and you basically have this really long tube, and inside this tube you have a magnetic field going down, and you have an electric field going down, So you also happen to have a bunch of particles, and you don't know what they are yet, but you send them through the cathode ray, and they go perfectly straight. But you find that if you manipulate the magnetic or the electric field a little bit, you'll find that actually the path of the particles will begin to... Actually, you know what? I'm going to use a better color for this one, green, because green is just a disgusting color. But you discovered that if you change the field a little bit, you discovered that actually the path of the particles start to change, and the spot that the light lands on at the far end of this tube on a plate, the spot starts to change. So you know that the way that you're manipulating the field is actually affecting the way that the ray of particles is passing through the tube. So you're like, oh, I'm going to design an equation for this now. And so you throw a bunch of things together, and it's a little bit like this. So, where y equals the deflection of the particle, Q, of course, goes on top, because the stronger the charge, the easier it is to be affected by the field. And then, of course, to that same end, E is also on top, because the stronger the field, the stronger the push is that will push the charge. L squared is also in the numerator, because the longer the tube, the more ability the field has to push it along. So the more time, the more space it has to push it along, so that by the end, the total deflection is greater than it would have been. And then, of course, in the bottom, you have M for mass, because the heavier the particle, the harder it is going to be to move, and the velocity squared, because if you have a fast-moving particle, then it's going to be hard to push. I mean, like, can you imagine trying to push, like, a speeding vehicle off the road? Don't try that. How much? It's dangerous. You're going to get yourself killed. So here's the equation that he came up with for the deflection of the particle, where y equals deflection, q equals charge of the particles, E equals the electric field strength, length is the length of the plates that it's running along, and then mass is the mass of the particle, and velocity is, of course, the velocity of the particles. But now he's like, what is this strange particle that I've been working with? So you are like, you as JJ Thomson want to find that out, and you're like, I'm going to manipulate my equation until I figure out what it is. So you know that if you manipulate either the electric field or the magnetic field, then the ray is going to move to one side or the other. So you know that there must also be a point where the magnetic field equals the electric field, and when they cancel out, that means that's perfectly straight. So you write down that, oh gosh, what is that? Golly. Maybe a trusty pen and paper is the best way to go, after all. So you write down Fe equals QE, which is equal to FB equals QVB sine. And you're gonna and since they're perpendicular in this case, because as we know from the definition of crossed fields, the magnetic field and the electric field is always perpendicular, you know that this is 90 degrees, and so you can cancel that out. So then you can also cancel out the charges, and so you're left with E equals VB, which you can rearrange to mean V equals E over B. And you're like, well, that's pretty good, but that's not good enough. I want to do more. So you connect it with this equation, and you write down that, and you replace the V in the deflection equation with this V that you've just figured out. So you say that Y equals the charge times E times L squared over 2M E over B squared, which I'm going to write as E squared over B squared. So of course you can cancel out this top E, and you can write it as Y equals Q L squared B squared, flipping the B to the numerator, over 2M E. And then you're going to manipulate this so that you are going to put M over Q. This is what's known as a mass to charge ratio, which is basically the ratio of mass of the particle to the charge. And this was important for identification of the particle itself. But so you manipulate it so that M is in the numerator, Q is in the denominator. Then you, of course, you take Y and you put that in the denominator. So in the end, you have B squared L squared over 2M. Oops, sorry, not M. 2Y E, and that's your final equation. And this specific mass to charge ratio was important in identification because this is what's known as the elementary mass to charge ratio, which is what became the ultimate identifier of what is known today as the electron. Hooray! It was all because of this guy.